Hi, so the last technique that we are going to talk about in the context of regularization is dropout. So let's see. So we just saw that ensemble methods are good, right? So what does that mean? That if we average the output of several models, then it always helps, right? But now in the context of deep neural networks, this is of course a challenge, right? So if you have to train several large neural networks, then it is going to be prohibitively expensive, right? Because then you are going to combine these neural networks, but then you have to train so many of those, right? And there are two options here, right? One is you train several neural networks having different architectures. So that's what I've shown in the first figure here, where you have all of these are neural networks, but they have different architectures. Or the other option is that you have the same neural network, same architecture rather, and you're going to train it using different subsets of the training data, right? Now both these options are obviously expensive, right? Because training a deep neural network is going to be expensive, and now you're talking about training K of those, right? And even if I were able to train K neural networks, at test time again I have a problem, right? Because in test time typically I need results faster, but again every test instance that I'm going to get, I'm going to pass it through all the K neural networks and then combine their output, right? So it's not just at training time I have to have a lot of compute, but even at test time I'm going to have a challenge, right? So how do we then use this model averaging idea, which we just saw in the last video, is useful? How do we use it in the context of deep learning, right? So the two challenges are that at training time your cost is high, and even at test time your cost is high, right? Irrespective of whether you use option 1 or option 2, right? So dropout actually addresses both these issues. So what it does is it effectively allows us to train several neural networks without incurring the cost of actually training K neural networks, right? And we'll see how exactly it does that. And it also at inference time, we don't need to pass the test instance to several neural networks. We just need to pass it through one neural network, but just do a simple trick to get the averaging effect, right? So we'll see how that works. So the idea in dropout is that you have this original network, which I have shown on the left hand side. You drop out some units from it. That means you drop out some neurons from it. So this is, I have dropped down some randomly some 6 neurons from here, and then you get a different network, right? So you have got a different architecture now, right? So just as in option 1, you were training neural networks with different architectures and you were training K of those. I've got the same effect here by dropping some neurons, right? I had the base architecture, I've dropped some neurons, and now my neural network looks a bit different, right? And you're just doing it temporarily. Just for that current training instance, I'm going to drop a few neurons, or that batch, mini batch, I'm going to drop a few neurons, right? And then again do something different in the next batch, right? Now each node is retained with some fixed probability, right? So every time I get a mini batch, for every node I take a decision whether I should drop it or retain it, and this decision is taken with a fixed probability, right? That means with 80% chance I'll retain it and 20% chance I'll drop it, right? So that's the decision that I take. So at every time I receive a mini batch, I visit every node and decide whether to drop it or retain it. Of course, it's not done like sequentially the way I'm saying it. You have more efficient ways of doing it, but conceptually this is what you will do for every mini batch, right? Now suppose the neural network has n nodes, then using this dropout idea, how many neural networks can you create, right? So I have n nodes given to you, and for every node I can either retain it or drop it, right? So it's a binary decision I'm going to take for every node, and each such configuration gives me a new neural network, right? So I just think of it that I have these n nodes here, right? And I'm going to write a 0 if I'm going to drop that node, and a 1 if I'm going to retain that node, right? So now this is my n-dimensional vector, and this will decide which neurons here get dropped or retained, right? And there are such 2 raised to n vectors that I can construct, right? Which means there are 2 raised to n networks that I can construct from a given neural network, right? So if I use the dropout idea and if I have n neurons, then I can actually construct 2 raised to n different neural networks, right? But then how does it help me? I just said that even if I have like k different neural networks, and k was of course much smaller than 2 raised to n, then I have a challenge in training it. So now I'm talking about 2 raised to n different neural networks which are possible. So how am I going to train these many networks, right? So the trick that we use is that you share the weights across all the networks. So you have 2 raised to n networks, but the weight matrices are the same, right? So now suppose this weight exists or this node is retained, suppose in such 2 raised to n by 2 of the networks, right? Because half the networks, if you are retaining and dropping with 50% probability, then half the networks would have this node, half the networks would not have this node, right? So that means this weight will be retained in half the networks, right? But this weight would remain the same in all the networks, right? I'll be using the same copy of the weight. That's the first trick I'm going to use. What's the implication of that, we will see soon. And the second trick that we are going to use is that we are going to sample a different network for each training instance. So it's not that I'll have like these 2 raised to n networks created at beginning and then train all of these 2 raised to n. I just have one network. Whenever I get a mini batch, I'm going to sample one of these 2 raised to n networks. That means I'm going to randomly drop some nodes in the network and then train using that network, right? So let's see what that means, right? It's like a bit difficult to understand, but we'll break it down into steps and then it should become clear, right? So we initialize all the weights of the network. So there are in this network, this is my base network, right? I'm not creating multiple copies of this. This is my only network. So whatever weights are there, so let's assume there are n parameters everywhere, n nodes everywhere. So you have n cross n weight sitting here. You have an n cross n weight matrix sitting here. I'm ignoring the biases for a while. And suppose you have only one output neuron, then you are n weights sitting here, right? So all these 2n square plus n weights I have initialized, okay? And I have started training. Now, I receive the first mini batch for training and I just drop some nodes from the network, right? So I've got a thinned version of the network for the first mini batch, right? And now I'm just going to assume that this is what my neural network looks like and just do my forward propagation and backward propagation, right? So I'll compute the loss using forward propagation and then I'll back propagate. Now when I do back propagation, which are the parameters that need to be updated? I had n square plus n parameters. Now if I do backward propagation, which are the parameters that I should update? Yeah, only the ones which had participated in the computation, right? So this parameter, for example, was not there. This was because both these nodes were dropped, so this parameter was not there. This parameter was also not there. This parameter was also not there. So obviously they did not participate in forward propagation, so they will not get updated in backward propagation, right? That's as simple as that. So let's see what that means, right? So these were the ones which were active, so these will get updated, these will get updated, and these will get updated, right? The other weights will not get updated, and it's a bidirectional error. That means in the forward propagation also these only participated, and in the backward propagation also only those will participate, right? So this is what I have done for the first mini batch that I received. Now when I receive the second mini batch, I again sample a new neural network from my original network. That means I just drop some other set of nodes, right? Because this is a random process. At every mini batch I'm going to decide for every node whether to retain it or drop it. So my decisions would change from one batch to another and I'll get a different version of the original neural network. And now again, I'm going to update only those weights which actually participate in the computation, right? And now if you look at it, right, so let's look at some weight which was there, this one, right? So if you look at this weight, this was present in both the networks. There were some other weights also which were present in both the networks. Maybe I should use a different color, right? So this weight participated in both the networks. So let me just call that weight as W, okay? At time step 1, I had updated the value of W using whatever update rule I wanted, right? Let's assume I was just using gradient descent. So my value of W has changed. Now at time step 2, since my weights are shared, I will start with the updated value of W. I will not start from W naught. I'll start with W1 because that weight has already been updated and then update it again using this equation, right? So that's what sharing weights means. These are two different networks conceptually, but actually it's the same network from which certain weights have been dropped, right? And those weights which were participated in the first batch as well as the second batch, for those weights I have done 2 updates, and for those weights which only participated in the first batch or only participated in the second batch, I would have done only 1 update, right? So the main thing to notice here is that even though it looks like I'm using a different neural network at every time step, it's not the case because the weights are the same. They are the shared weights, and I just start from the previous value of the weight which was at the say the kth iteration, and then update that value. I don't start with the value which was at the 0th iteration, right? Okay. Yeah, so that's what is being said in this slide. So each thinned network will get trained rarely because there are 2 raised to n networks, right? So it's very unlikely that this network, if n is very large, right, which is typically the case, that the same network will get sampled many times because there are 2 raised to n different configurations possible. It was also possible that some of these networks will never get sampled at all, right? Because if your number of steps which you run the data for is less than run the training for is less than 2 raised to n, right? Suppose you have a million nodes, 2 raised to million is going to be very large, and you're going to train for much fewer steps than that, right? So all these 2 raised to million networks will not even get sampled. Some of them would get sampled, right? But still, because of this weight sharing, it's like every network is getting trained, because even if this network was never sampled, there were other networks which got sampled in which these weights would have been active, and hence those weights were getting regular updates, right? And since every weight is going to be present with an 80% probability, because you're going to retain 80%, with probability 80% you're going to retain a node, right? And also, okay, so 80 into 80, because both these nodes need to be remained. So with 80% probability this will be retained, and with 80% probability this will be retained. So with 64% probability both will be retained, and hence this weight would be retained, right? So every weight with 64% probability it will be retained, right? And hence it will get updated many times. It will get 64% of the times that you are doing training, it will get updated. So if you run for 1000 steps, every weight will get updated around 640 different times, right? At least 640 times, okay? Yeah. So now what do you do at test time? This is what you are doing at training time. At training time, every node was present only with probability P, right? Now, what do you do at test time? At test time, now again you cannot sample these 2 raised to n networks, pass the output through all of those, and then take the final decision, right? So at test time you can use this neat trick, which is saying that, hey, every node was only present with probability P. That means it was only present P fraction of the times, right? So let's say 80% of the times or 60% of the times, whatever is the probability that you have chosen, right? So then I should trust the output of this node with only that fraction. This guy only participated in 80% of the discussions. So whatever it says, I'll only trust it with 80% value. That's the same as saying that whatever output this guy gives, just scale it by that fraction. As simple as that, right? So you participated only in 80% of the discussions, so I'm going to trust your output with only 80% confidence. That's the same as saying that whatever output you give, which is going to be passed to the next layer, I'm just going to scale it down by P, right? So that's all you do at test time. So again, at test time, you're just passing through a single network, and every weight in the network is going to get scaled, or the output of every neuron in that network is going to be scaled by this probability P, right? That's all you're doing, right? So now let's try to get some more intuition, right, into what dropout is actually trying to do and why does it act as a regularizer, right? So it actually applies a masking noise to the hidden net. So what does that mean is that in every, you could think that suppose there are n vectors, n nodes here, at every mini batch I am creating an n dimensional vector where some values are 1, say 80% of the values are 1, and the remaining 20% are zeros, right? And that's the same as whatever output you produced here, I'm going to multiply this by this mask, right? So if you were masked out, then you are not going to participate in the computation. That means your output would be zeroed because I'm just multiplying you by this mask vector, right? So that is what is happening here. Some units are getting dropped, and this is how you actually implement it. It's not that every time you visit every node and decide whether to keep it or not. You just create this random vector by saying that I want 20% of the units to be off, and then at this layer, whatever output you have computed, you just multiply it by this mask, so 20% of the outputs will be set to 0. That's the same as this node not participating in the computation at all, right? Now, when you're masking it, what is it that you're effectively doing, right? So what happens is it prevents the nodes from co-adapting, right? So what does co-adapting mean? That if you have all the nodes active, then there could be this one lazy guy who says that, okay, I mean this other guy, suppose I'm trying to detect faces, and this other guy is going to detect noses, a nose and someone is going to detect eyes, and I don't need to do anything then, right? I can slack. I did not actually work much. The other guys can do the work, right? So that's what co-adapting means, right? Or it could be that, hey, you detect nose and I will detect eyes. I will only fire if there is a clear eyes in the picture. If it's taken from the side, maybe the eyes are not visible, and you fire only when there is nose, right? Of course, it's not that the neurons are talking to each other, but this kind of co-adapting could happen where every neuron just focuses on doing one thing, right? But now if you are going to drop the nodes randomly, right? So what will happen in that case? Suppose this was the guy which was focusing on detecting noses. Now you have received a training instance, and that training instance, say it has a nose, right? And you have dropped this guy out. Now there is no node in this layer which is detecting noses. Hence the other guys will have to wake up and say that, hey, I cannot rely on anyone else, I cannot co-adapt because this guy is unreliable. And sometimes he is active, sometimes he is not active. So better I also learn how to detect nose in addition to learning how to detect, say, eyes, right? So every node will now have to act independently and take more responsibility, right? So this is what actually happens in Dropout, and I'll just now flash the content on the slides. Yeah. Yeah. So either the multiple nodes need to learn how to detect noses, or other nodes need to learn how to detect noses, how to detect the face, even if the nose detecting neuron is not active. That means some other node needs to now detect how to, detect a face using eyes. Right? So what the problem here is simple. Right? I'm showing you an image and I want to tell you whether there's a human face in it or not. Right? And you can use the features of a human face to detect. Right? So some neurons could fire if their eyes is there, some neurons could fire if nose is there. But now if you drop out things, then some of these guys will no longer be available. So then the other guys have to become creative. Then earlier maybe the network was never learning to rely on the eyebrows to detect a face. But now some neurons will start picking that up because the other guys are not working, so I better become more creative, right? So that way the network is becoming more robust, right? So that's all I had about Dropout. And what I'll do next is I'll quickly give you a summary of all the regularization techniques that we have studied.